Thanks for joining at sharply at 9:30. And today we are going to talk about the need for a power system simulation software and list of power system simulation software. Then modeling of generator transformer transmission line. We are not really going to touch much because already we have enough videos in our YouTube channel, so you can very well go and watch. So only what is needed for our today's topic, which we will see. So what's the key simulations which we are going to see is the three which we have already given in agenda: Ferranti effect, power factor correction, and OLTC selection. Fine, with that background, straight away we will jump onto this topic. Why do we need a power system simulation software? Answers are quite simple. Manual calculation for a complicated power system is almost impossible. If you argue that it is possible, then it is difficult. At least I would say that. Yes, and it is a time consuming and human error is always possible. This could be the three reasons why we can say we need to go for a power system simulation software. Manual calculation, if you want to do perform a load flow analysis for the entire Indian grid network, and I personally feel it is impossible. And if you are a super brain, yes, it's possible, but you tell me how much time you takes and what's accuracy of it, and assume I mean if it goes for say example 50-60 iterations, and how do you do the matrix calculation? So answer is quite simple. Why do we need any simulation software is simple. Means to reduce the manual work and reduce the time and reduce the human error. So that's the real reason why. Also, why do we need a power system simulation software? List of power system softwares. Yes, I have not really intentionally. I have kept means what to say many dots open. So means we are going to talk about only ETAP and DIgSILENT power factor in these 3 days. But I want you to understand from it three different perspectives. One, what are the simulation softwares which are used for a steady state analysis? When I say steady state, it's like load flow, short circuit, static motor starting steady, or harmonic analysis, relay coordination, or plus. So for this steady state analysis, what are the simulation tools which are used? And if it is a transient stability, electromechanical transients, where you are trying to find out the relative angle or critical clearing time, critical clearing angle. So then what's the software which is used for this electromechanical transients? And if you further go with an electromagnetic transients, then what are the specific softwares which are available for that? And now means what to say, even beyond simulations, we are going with the hardware in loop. You might be heard about quite a lot of vendors are offering a hardware in loop solutions. And then probably also the next level complete system is a scaled down version in a physical scale, like a real-time digital simulators. You might have heard about RTDS and OpenRT. The different dimensions of power system simulation softwares. Means one software will not fit for all the requirements. So it is very important what software you have to select for what studies is more important. So example, if you select PSCAD or EMTPRV for a load flow analysis, yes, that softwares can do, but uh, I mean, is it really worth investing that much time and effort to just perform a load flow? No. So means what is it? We will talk about that perspective. What is used for a steady state analysis? Why that software is better for a steady state analysis? And in what case you have to go for some other simulation softwares that we will discuss about tomorrow, right? That's great. So let me move on. I believe I have not put up a complete list of power system simulation softwares. Still, question is open for the participants. If you know the softwares list of simulation softwares, you post it in the chat box. And I request probably means what I will come up with a complete list of power system simulation softwares. At least about 50 commercially available power system simulation softwares are available, and there are about 25 plus open power system simulation softwares are available. I will come up with that complete list tomorrow. Anyway, which is not going to make much sense, but still I will come up with. But if you know other simulation softwares across the globe, yes, that you can watch. Right. Why do we need to perform a load flow? That's the topic today, right? Yes, I have given the answer. If you have not seen the answer, yes. So why do we need to perform a load flow analysis? So on a consolidated way, IEEE 399, the standard has given this is the answer. Load flow analysis needs to be performed to identify the component loading or circuit loading that is going to decide or dictate what's the equipment loading. Say example, if there is a transformer rating of 10 MVA, whether the transformer is loaded 70% or 60% or 30%, that's equipment loading. This also gives an additional information with respect to the transmission lines, what's the available transfer capability or available transfer capacity, that is ATC. So if the transmission line is able to carry 100 MVA, and if it is loaded with the 30 MVA, still how much capacity which is available, which I can use it for a future. That's the first point. So performing the load flow analysis to identify what's the equipment loading. In a radial systems, it is quite easy to find out the equipment loading by means of just adding the loads together and putting a load factor. But in an interconnected power systems, finding out the equipment loading without load flow analysis is almost impossible. Simple reason because means the power flow in a branches follows your impedance, and the current flow is dictated by the impedance offered by various lines. That means power from the source to the load centers, it has a multiple paths. It can flow in whatever may be the path which is convenient for it. So it will take based on the impedance, the power will flow. So it is absolutely important to perform the load flow analysis to find out what's the equipment loading in each and every branches. In a radial system, it may not be much stressed because you can easily find it out without even load flow. But in an interconnected system, it is a must. And when there is any one equipment outage, that's basically a contingency analysis, then how this power is transferred to the other branches, that's also you need to see. So component and circuit loading is not necessarily in a normal operating condition, but also in the n-1 contingency where one equipment out of service, or n-2 contingency where there are two equipments out of service. Okay, fine. So then probably moving to the second point, it is helping you to identify what is the bus voltages at each and every buses. Yes, without performing a load flow, you may not be able to identify what are the voltage profile at each and every bus. So this is another important aspect of load flow analysis. When reactive power flow, that of course means it covers as a part of component or circuit loading itself. The load flow analysis is helpful to find out both real and reactive power flow. When I say that it is real power flow, reactive power flow, current, power factor, means you can talk it in whatever may be the sense you want. And in a load flow analysis, help you to identify the transformer tap range requirements, whether I can go with plus or minus 10 percentage tap, or whether I have to go with minus 5 plus 15, or whether I have to go with minus 15 percentage plus 5 percentage tap, can be identified only using a load flow analysis. Means if you know what is the voltage fluctuation at the grid side and what is the load changes in the load side, probably you will be able to find out what's the transformer tap range which is needed, that we are going to see with some simulation example today. So this load flow analysis also helps to find out the losses in each and every branches, like a transformers, transmission lines, etc. And of course, it also gives the what's the total losses in the systems. When we talk about this total system losses, this also provides an additional information. What's the optimal configuration which you need to run your system so that the losses are minimal. So let me repeat my statement. Load flow analysis is going to help you to identify the losses in the system, the total losses in the system, as well as the individual equipment losses. So this also helps you to identify what is the optimal configuration which you have to operate your system so that the losses will be minimal. So that's where your load flow helps further. And to take about other question, means generator, exciter, regulator, voltage set points. Yes, this I have not really planned some simulations, but I will try to put up some simulations for this to answer better. If there is a generator of 500 megawatt, whether it has to operate in a voltage control mode or MVR control mode or power factor control mode. If it is operating in a voltage control mode, whether I have to set 100% voltage at its terminal or 101% or 102%, all this has to be answered. This can be optimized using a load flow analysis. So I have not really planned a simulation, but if time permits, we will do that simulation also. And performance under emergency conditions, that is means contingency conditions which I have talked about, n-1, n-2, etc. Where your power flow will be different, your voltage will be different, losses will be different. So your system may go means out of control. So all these things which you can check in the load flow analysis. Right. One most important point IEEE 399 misses, or because IEEE 399 is not really covering that person, is steady state stability, because IEEE 399 is talking about power system analysis for industrial and commercial power systems, right? So in industrial or commercial power systems, the angle separation is not far, like means all the equipments are within, so power flow is within a small place, so the angle difference between sending and receiving end voltage is not much. So that's the real reason why they have not really covered it. But one important aspect which you need to work out or verify in a load flow analysis for a large scale interconnected power systems, like when you are performing the load flow analysis for the entire India, then you need to really look at means what to say, steady state stability angle, steady state stability also. That is steady state stability by means of checking the angle of each and every buses and finding out what is the maximum angle difference between two different buses. So that you need to check. Fine. So this is purpose of performing load flow. So to quickly conclude, why do we need to perform load flow? To find out the equipment loading, to find out the voltage at all buses, to find out real and reactive power flow, so that the power factor corrections also can be can be talked about to find out the transformer tap range, minimum tap, maximum tap, etc., to find out the losses of the systems, to set the generator terminal set point voltage, and to check whether the system is okay during contingency case or emergency conditions, and of course to find out the steady state stability limit. Right? Yes. Fine. I will go ahead. As I told, modeling of transformer and transmission lines, generators, I'm not really going to talk much on this simple reason because we had enough videos that might be repetition for you. If you go to our YouTube channel, you can find n number of videos. I believe you are in already our channel only, you are watching it. So if you go to our channel, you can find, yeah, n number of videos on transmission line modeling, transformer modeling, transmission line modeling, right? Generator basics and modeling, transformer modeling part 2, grounding of generators. So we have talked a lot, so I am not really going to touch today means what is the modeling of generator, transformer, transmission lines, but when we are doing some simulations, probably you can really means what you say, ask your questions. And if you have in-depth questions, probably in the modeling of generator or a transformer or a transmission line, I request you to go back to our channel after this session. And we have means 2 sessions for transmission line, 2 sessions for a transformer, and 1 session or 2 sessions for a generator. You can very well watch that. Yes. Now there is a question. So Ferranti effect. So what is Ferranti effect? IEEE 399, which I am mentioning, is not a standard for a load flow. That is an industrial and commercial power system simulation. So means it is not necessarily exclusively for a load flow. IEEE 399, what I have talked about, is talking about means what to say, all power system analysis, that is load flow, short circuit, motor starting, relay coordination, etc., for industrial and commercial systems. And now probably you might have heard IEEE 3000 series standards, IEEE 3000.2, that is exclusively talking about load flow, right? So means you have quite a lot of IEEE 3000 series which is means very recent, that you can refer, Ganesh Kumar. And there is a question from Abhijit Kumar. Please provide various Indian and international standards for a load flow. I think that's also a question. I have answered it. It means what say, you can refer either IEEE 399, that is for when you are performing industrial and commercial power system analysis, and probably for a generic power systems, you can refer IEEE 3000.2. Yes. So let me go on. If I have any answers for, yeah, there is another question. How to do dynamic load flow in ETAP and DIgSILENT Power Factory? You have an option, means time domain load flow analysis. You can very well use that time domain load flow analysis in ETAP and DIgSILENT Power Factory to perform. So let me straight away jump to the simulation software. I'm in ETAP 19.5. The latest version of this software is ETAP 20, which I yet to install, which came by about a week back. Yes. So straight away I'm going with Ferranti effect. So Ferranti effect we generally define a simple manner, like receiving end voltage is higher than sending end voltage. Is it just with that? We will try to address all with some simulations. So I have taken simulation for Ferranti effect. So when I said it that, what's the typical voltage which I need to choose for my system to simulate Ferranti effect? Shall I use 415 volt? Shall I use 11 kV? Shall I use 110 kV? Shall I use 400 kV? Or I have to go for 765 kV or 1200 kV? So now I have modeled a system with sending in bus, probably bus 1, and receiving in bus, that is bus 2. I have yet to enter the value for a voltage, that is decides what's the voltage of that particular bus, and of course the transmission line. Now question is, when we talk about Ferranti effect, what's the voltage level which we need to talk about? Is it appropriate to talk about Ferranti effect at 415 volt, or I need to talk about a medium voltage like 11 kV or 22 kV, or I need to think of 110 kV or 220 kV, or I have to go with 400 kV or 765 kV? Yes, when we talk about Ferranti effect, the first and most important which we need to understand is this happens in a high voltage and extra high voltage. It never happens in the low voltage systems. Okay, so means what is it? The ideal voltage is 220 kV and above. Yes, somebody has really put it right. It has to be high voltage or an extra high voltage, right? Or probably even ultra high voltage, whatever you call. And you may appreciate the fact that India has 1200 kV already. That is the highest AC transmission system voltage across the globe. Let me repeat my statement. 1200 kV transmission system, AC transmission system, which is available in India. That is the highest voltage, highest transmission system voltage in the AC system across the globe. Right. That's just an information. Yeah, if you like that information, yeah, you put it. Yeah, I like it so that I can understand. I can, I mean, sort of say, throw quite a lot of such informations as and when I am flowing with that. Yes. Now, I have modeled my system as a 400 kV. It is not necessary that it has to be 400 kV. It could be, means 220 kV. It could be 380 kV. It could be 550 kV. It could be 765 kV. It could be 1200 kV. Whatever it is, but it happens in extra high voltage. That's perfect. Okay, so now we have understand Ferranti effect is just not about receiving in voltage is higher than sending in voltage, but it's also important to understand. I mean, this happens only high voltage and extra high voltage. Yes, that's the first point which I have made. Okay, let me go to my second point. I have a transmission line, right? What's the length above which this Ferranti effect occurs? Yeah, shall I give it at say 100 kilometers, 50 kilometers, 10 kilometers, 5 kilometers, or 100 meters? Or into go with the 200 kilometers, 300 kilometers, 500 kilometers? What's the length which I need to put? That's the first question. I mean, when you are answering it, let me go to the other answer as well. How to find out this transmission line parameters? Here there is a R, that is a resistance, and there is a reactance X, and Y, that is a susceptance. So if you model your transmission line in a nominal pi, you might be having resistance and reactance in series and your conductance and susceptance in the parallel. So means R is given, that is in ohms per kilometer, X is given, that is in ohms per kilometer, Y, that is equal to G plus JB, G plus JB. So I mean, so to say, we are assuming G, that is a conductance, is 0. So Y in ETAP software is just meant only the B, that is a susceptance, right? Yes, I got the answer for the length. So everybody has put up, but yeah, some good answers. It should happen only in the long transmission line, right? It cannot happen in a short transmission lines. So we will simulate and validate all those. Okay, but before going for it, done. Second question probably means what's the resistance, reactance, and susceptance values which I need to enter here. So if you have an answer for that, you just trying to answer that questions. What is the resistance value which I need to give? What's the reactance value which I need to give? What is the susceptance which value which I need to give? And if I do not know these values, how to calculate these values? That's another question. And of course, length. Everybody has talked about the length has to be more than 100 kilometers, around 50 kilometers. I go with my favorite example of 300 kilometers. Right? That's perfect. But I'm coming back to this question. Is this video is blur? Absolutely might be, but that's because I'm using software. Means if you are using from your mobile, yes, you might be right. I request probably the people, those who are watching in I mean laptop or a desktop, please make sure that, because that's obvious when we are going for a software, that could be some blur. So you can probably enlarge to the full screen when you are watching in laptop or a desktop. That helps you to better understand the video when I'm going for a simulation. When I'm in a presentation, it may be okay, but when I'm in a software, I cannot do anything. That's the best possible what we can do. So those who are using in mobile might be feeling difficulty. I'm not denying it. If you are using it in a laptop or a desktop, please kindly ensure you are going to the maximum possibility. Okay, fine. So right, that's thing. Okay, so let me try to answer that question. I have given the line length as 300 kilometer. That's fine. So now the line length, if I want to display, there is an option, display option, where I can display the line length. So line length is 300 kilometer, right? So you can watch that. And 300 kilometer is I have given, but I need to enter what's the parameter, which I do not know how to find out the parameters. There are two ways of it. If I know the parameters, I can straight away enter the parameter by means of clicking user defined, and I can give what is the resistance at temperature T1 and what is the resistance at the temperature T2 and what is the reactance value and what is the susceptance value. That's one way of doing it. If I know this parameter, if I do not know the transmission line resistance, reactance, and capacitance, then I have an option to calculate it. I mean, if you are a student, if you have studied a subject transmission and distribution, probably chapter 2, you might be talking about line parameters. That's all about what we have to do. For that, you might be writing like L, transmission line inductance is equal to 2 into 10 power minus 7 ln GMR by GMD, etc. So for that you need to specify conductor parameters, that what is the conductor size, that's to find out the resistance, and you need to select whether it is a copper or aluminum, so that is to find out the resistivity and many more. And of course you need to check what is the tower configuration, whether it is a horizontal configuration, vertical configurations, etc. So that's all probably you need to enter. So let me go ahead with entering some data. I am entering the data of a phase conductor, that is RYB phase conductors. So I am selecting some conductors. So I have selected unit as metric systems and I am using at 50 Hz. There are different conductors like AAC, AAC, copper. So you can choose whatever may be the conductor which you want. If you change the metric to ANSI, this is by default library which is available. Don't ask me why ACS or aluminum conductor steel reinforced is not available at metric in 50 Hz. This is what the library has. You can very well create your own library, right? So I have selected AAC conductor, all aluminum alloy conductor, and I have selected 1450 square with 91 strands as my conductor size. So it's a 400 volt 400 kV, so I have selected a large size conductor. Yes, and I have to select the ground wire also. So here I am choosing some ground wire with again 37 strands of about 1200, or even if it is less, probably I can choose 19 strands. Don't ask me why I am selecting 60 Hz. Means the software doesn't have any standard library at 50 Hz. If you have, you can develop. You can very well create it and you can use it. So somehow I have selected what is the conductor size. So that means what is the conductor resistance, what is the conductor GMR, all these informations are available. Similarly, ground wire I have selected. All right. So configuration, yes. So it's just not important to find out and tell what is the parameters of transmission lines and uh, means what is a phase conductor and ground wire, but also equally important to tell what's the tower structure. That basically decides what's the height, what's the spacing between the conductors, what's the spacing between the ground wires, what's the spacing between ground wire and your conductors, etc. So now I have selected horizontal, which you can see in the right hand side. There are three dots ABC. There is a horizontal configuration. If I change it to vertical configuration, yes, you can find the vertical configuration. And if you want triangular configuration, there are different configurations which the software offers, and you have an option to select on your own as well. So it's all purely depends on you. How do you so to say, want to model your transmission line? Yes, fine, right? So I have given I'm going with my experience, and if you have a data of what's the approximate height of 400 kV tower, you can give it. I am giving 24 meters, but if you know what is the height of 400 kV tower, you can answer it. So I have given 24 meters as height of the tower, and 6 meters is a spacing between the conductors. That means R phase to Y phase it is 6 meters, Y to B it is 6 meters, and then hence R to B is 12 meters. That's obviously it comes. So now the height of the tower which I have given is 24 meters, and spacing between the conductors I have given 6 meters. Right. Now number of ground wires I need to enter either 1 or 2. So means what say 400 kV, you have to tell me now how much ground wires you might be having in a 400 kV systems, whether it is 1 or 2. Okay, it's not a topic today. I mean we will discuss that in a separate forum, but yes. So I have selected 1, and if I am giving this height difference between your ground wire and phase conductor, which I have given as 5 meters. If I am changing the number of ground wires to 2, then I need to give two important parameters. One is what's the height between your ground wire and phase wire, and what's the distance between these two ground wires. So if I'm putting it, probably I'm giving say example 8 meters, right? Okay, this is the data which I have given. With this data, the software automatically find out the transmission line parameters. So this is what means ideally you are doing in a transmission and distribution subject. In a manual calculation, you are writing like L is equal to, as I told, 2 into 10 power minus 7 ln GMR by GMT, something like that you are doing. That is precisely what the software also does. But probably when you go with that calculations, when you will be having more than means what say RYB, if you have a double circuit, or if you have a 4 circuits, if you have with multiple ground wires, etc., then your matrix size will be much difficult to calculate, but the software automatically provides you the data. So you can, if you are doing something manually, you can very well validate this, validate with this. So resistance, reactance, susceptance, all these parameters which I have identified. So this also gives a beautiful idea of what is the positive sequence, negative sequence, zero sequence. You can see positive sequence is 0.02395 ohms per kilometer, that is a resistance. Positive sequence and negative sequence is equal for resistance, reactance as well as susceptance. But if you look at the zero sequence is not really same, and our theoretical books will talk about this zero sequence will be approximately 2.5 times to 3.3 times or something. But answer is, I mean, it is not necessary. That's just a thumb rule. So you can exactly find it out. Now you can talk about another aspect as well. So means what to say, you might be heard of something called transposition. So means what to say, this is a parameter of resistance, reactance and susceptance per ohm. So you can look at these parameters in phase domain as well as in a sequence domain. So you can see here, I mean, I am seeing it in a positive negative sequence for all, for resistance, reactance, susceptance. This all possible in sequence domain, and a phase domain also you can find some data. Yes, now this line is not transposed. If you transpose this transmission line, if you transpose this line, then you can very well come back and you can watch what happens to this matrix, right? You can find the values only in the diagonal, right? This matrix becomes diagonal matrix. I am not going to talk about I'm not going to really talk about I mean why is the diagonal matrix, etc. This exercise very well you can take download the demo software of ETAP and you can practice it, and you can find out why it is coming. Okay, so let's jump on to our topic. Now we have modeled a 400 kV bus with transmission line of 300 km with transmission line parameters. Now question is to put a Ferranti effect um, means what's the load which I need to connect, what should be the load which I need to connect to simulate the Ferranti effect. Before that, I will try to answer a question from Sneha. Why positive and negative sequence values are same? Positive and negative sequence values will be same for all your static equipments. That means for your transmission lines, cables, transformers, etc. Means you take any static equipment which is not rotating, that is except motors and generators, you will be having same positive and negative sequence for all the equipments. There is a question from Ramesh Krishnan. Is that possible to find a transmission loss in the software tool? Okay, he's asking corona loss. No, this is not a tool to find out a corona loss, but you can find out the copper loss in this tool, I square R loss, that I am going to anyway explain. Yes, fine. So I think I mean if I have an answer for this question, I mean what's the load which I need to connect? Yeah, light load or no load. So I'm going without any load. I'm going without a load and I'm running a load flow analysis. I'm just clicking this load flow analysis button, and you might be having quite a lot of options like Newton option, fast decoupled, adaptive Newton option, and probably if you are familiar with the previous versions of ETAP, you might be having an option Gauss Seidel, which was what we are studying in the college. But I am not sure means why the ETAP has means eliminated that Gauss Seidel model altogether in ETAP 19.5. They have not even given the option which you can see. Gauss Seidel model is not really given here. They have adaptive Newton option, but Gauss Seidel is missing. Okay, answer means we are not going to focus more on these models. Means we are going to worry more on the results, right? But anyway, means all the models has to be, means methods has to be used at appropriate time. Yes. So I have run something and it's giving a results. This result is no meaning unless otherwise I add units, right? Yes, I have added units. Now, what's the conclusion from this? I believe let me zoom it a bit more so that at least it's something visible for you. I know there is a difficulty when I'm going for a simulation software, but yes, I mean, so to say, slides I can do something, but simulation software I cannot do anything else. Yeah, I believe screen might be at least visible with respect to showing the numbers of the voltage or kilowatt or kVA. Yes, perfect. So now 400 kV. 300 km transmission line. If you want to display the line length, let me again display it. And if you want the impedance, I can display the impedance also. There is no load connected, but still you can find there is about a 335 kilowatt loss. There is about 335 kilowatt loss in your transmission line. Means there is just a 300-kilometer line. There is no load connected. Correct? No. This 335 kilowatt is going to the line. What does that mean? That's the loss in the transmission line. Somebody has put up. Is it possible to find out the losses? Yes, you can very well find out the losses. So this is the loss. Here I have not connected any loads, so means what say loss is same as what's the power flow which is here. So the loss is 335 kilowatt real power and the loss is minus 152 MVAR, minus 152 MVAR. That is about I mean reactive power loss. Since reactive power loss is means in negative, which means this is a reactive power gain. That means the transmission line is injecting reactive power of 152 MVAR. Why it is injecting? That's because of shunt capacitance. Somebody has put up about question of angle, phase angle. Yes, thanks a lot. I'm not sure what's his name. I am probably scrolling down a lot. So yeah, thanks a lot, Satyanarayanan, for asking that. Yes, yeah, I got this. So I have plotted that results with that angle also for your convenience. Yes, now angle is also visible for you. That's great. Yes. Fine. So means what we have modeled now is like we have modeled a 300-kilometer line, no loads which is connected. Means resistance reactance which is identified using transmission line parameters by means of giving a configurations and transmission line parameters. The loss is 335 kilowatt. I mean we may not really worry about this 335 kilowatt loss unless otherwise I tell another factor. Means with this 335 kilowatt probably you may be able to means what to say electrify at least 3 or 4 small villages, right? Probably the transformer which you might be seeing near to your home is 100 kVA or 200 kVA. That means you can feed I mean 3 or 4 such transformers with this capacity. Imagine how much homes which you can electrify. So, and if you have not really understood that, probably let me take another way to prove I mean what is the significance of the 335 kilowatt loss. Yes, if I am putting it in numbers and price, you can understand. So 335 kilowatt is the loss. If the system is running for 1 hour, right? This is kilowatt. This is hour. And I mean, what's the energy? That is power into time, right? So this is the kilowatt hour. So that is unit as well, right? So 335 units is the loss in 1 hour. So if I am assuming the price as say example 8 rupee 5 paise, which is a tariff for Tamil Nadu for commercial users, then loss which is incurred in an hour is about 2696 rupees. That is just for an hour. That is just for an hour. And if you look at, I mean, what to say, for a day, and just multiplying by 24. So knowingly or unknowingly you are losing 64,000 rupees just by means of energizing a 300-kilometer line and keeping it on. That's it. As simple as that. So you might be losing about 65,000 rupees. That's not definitely a small number. Yes. Fine. So the system has also another problems like this 300-kilometer line injects about 152 MVAR. So instead of means what is the kVAR, if I am putting it in MVAR, then you can understand that, yes. So you can see the system injects about 152 MVAR, 152 MVAR, right? That's great. Okay, perfect. So is that the only other issue? No, absolutely no. You can look at the receiving end voltage. I mean, so say in a 400 kV, as per Indian grid code and CA regulations, you have to maintain the voltage within plus or minus 5%. That means only the voltage of 95 to 105 is allowed, but you can see the voltage has gone beyond 105%. So that's also a real reason why the bus is in red. And if you put it in a kV instead of percentage, yeah, it is 422 kV, only 420 kV is acceptable. So how to mitigate the Ferranti effect that everybody knows? You can put up shunt reactors, right? You can put up shunt reactors to bus 1 as well as bus 2 in a real time, but here in a theoretical case, you can, I mean, what's very well put in bus 2 to validate it. Okay, I'm instead of that, I'm trying to add some loads, but yeah, multiple slack bus is possible. Yes, that is possible in almost all simulation softwares. all simulation softwares, and ETAP also supports. You can go with a multiple slack bus. And if you want me to simulate a multiple slack bus, what I do, I will add another slack bus here. Right, now I have two slack bus. If you want to check, this is also a swing bus or a slack bus. Here also it's a swing bus or a slack bus. Let me run a load flow. Yes, you can see now. Means for the still system is running. Somebody has asked the question: is it possible to run multiple slack buses? Yes, it is possible. So I have two slack buses now in the system. Previously, without this grid, bus 1 was a swing bus, whereas bus 2 was a load bus. But now bus 1 and bus 2 both are swing bus. If you are still not confident on my words, I will show you the report. We have two buses in our systems, and both the buses are swing buses. So that's about swing bus, slack bus, or reference bus. You can call both. Let me check whether the report is on. Might be taking some time. Yes, it is on. Yes, it's taking a bit of time. So you can see here number of buses. So two swing buses. Total buses itself 2, and out of that all the 2 buses are swing bus. That means multiple slack bus is really possible. Okay, somebody is telling Excel, close the Excel. Let me close this. I'm not sure whether it will solve the purpose. If it solves, that's great. Okay, so swing bus is 2, so that means multiple slack bus is possible. Yes, somebody has a question like what's the why the reactive power is in negative. So for that, let me resume back to the previous slide. That is, I have switched off this grid. So that means now bus 1 is a slack bus, bus 2 is a load bus. Why this minus 152? That is negative. That is negative, simple reason because that is injected by this one. So loss is 0.335. So 0.335 megawatt is flowing in this direction. So that is positive. And in a transmission line, you have a reactance that is in series, and you have a capacitance which is in shunt. Your capacitor injects reactive power, and that reactive power is flowing towards your grid U1, that is utility 1. So that's the real reason why it is in the reverse direction. So I hope that is that's clear now. Yeah, thank you. So the magic is working. Like when I am closing the Excel sheet, it is working. Thank you. Great. I am not sure what's the relationship between an Excel sheet and Echo. Yeah, good innovation. Thank you. Fine. So now I think I have made one point which is clear. Means what to say? What is Ferranti effect? Ferranti effect is in a long or very long transmission line during no load or light load conditions. The receiving end voltage is higher than sending end voltage because of shunt capacitance present in the systems. So let me repeat my statement. When somebody asks what is the Ferranti effect, your answer should not be just a simple VR is greater than Vs. No, your answer is in a long or very long transmission line where I have assumed 300 km now. In a high voltage or an extra high voltage systems, that is 400 kV or 220 kV or more, and during no load or night load, now I have assumed the no load conditions, the receiving end voltage is higher than sending end voltage. That's because of shunt capacitance present in the system, which I have modeled now. Right, so that should be the ideal answer for a Ferranti effect. Right, if I am changing the line length from 300 km to 1 km, let me check, is there any Ferranti effect? Absolutely no. You can see sending end voltage is also 400 kV, receiving end voltage is also 400 kV. So there is no Ferranti effect if the line length is less. Hope that answers. So essentially you need a long transmission line, and you do your exercise with the 415 volt or 11 kV. I am not going to do that. It's consuming time. Then you can find it will not happen in a low voltage and medium voltage as well. And probably let me add on to the other impact and aspect. Let me add a load. And let's see. So you tell me what's the load which I can put in a 300 km transmission line. So that I will put it to check whether I will be able to transmit that load. So let me keep it out of service now and I will run. But what I expect is what's the load which I have to connect, or what's the transmission capacity of the transmission line, and what's the power factor which I need to give. So now the 300 km line, so the receiving end voltage is 422 kV. That's Ferranti effect. But before that, if I want to show one more thing, this happens because of shunt capacitance. What I am doing, I mean, what to say, just trying to simulate one more case for you to prove that happens just because of shunt capacitance. If shunt capacitance is not there, then it will not have any Ferranti effect. To prove that, what I have done, I have made the capacitance value as sorry, I should make it 0, right? So now I have resistance, reactance and susceptance. You can see no load connected at the receiving end. Sending end voltage is 400 kV, receiving end voltage is 422 kV. That happened because of shunt capacitance. If I am making the shunt capacitance 0, let's see what happens. Yeah, of course. So now you are very clear, pretty clear. This Ferranti effect happens because of shunt capacitance present in the system. This happens because of shunt capacitance present in the systems. What I have done, I have just made the shunt capacitance as 0. As soon as I have made the shunt capacitance as 0, you can see, means what to say, there is no real power loss, there is no reactive power loss. The sending end voltage is equal to receiving end voltage because there is no current in the transmission line, right? So let me come back to this. Yes, I have added this. Now you are back to this. And probably if you want to look at the current during no load, means what to say, we assume that means when the receiving end is open, the sending end current we may expect sometimes because of Kirchhoff current law, the current is 0, but the current is 228 amps. This 228 amps is a simple reason because of the shunt capacitance. This is a charging current, or this is a capacitance current which is flowing in the line. There is no load which is connected at the receiving end. I used to pose this question most of the time in my interview. If I am not connecting any loads and if the line is length is around 300 kilometer in a 400 kV line, what is the sending end current? Most of the students, even probably the few experienced people, tend to answer it's 0 because the receiving end is open. But please always remember there will be a charging current of the capacitance because of the transmission line. That's fine. So let me move on. Let me add a load now, right? So now we have seen Ferranti effect. So somebody has given 300 megawatt 0.95 power factor. So let me put the same one. Yes, I strongly believe the session is for all of you. And if you have any questions, please post your questions. So let me keep megawatt constant and power factor is 95 percentage. It is 0.95. Here it is in percentage, so I have given it 95 percentage. So I have added a 315 MVA, that is 300 megawatt at 0.95 power factor. Right. So let me go ahead with the load flow analysis. Still I am getting the same results. Why? Because I have not switched on the load. Right. So load is off, out of service. So I need to bring the load in service. Yeah. Thanks. Now, yes, you can see. Is it possible to transmit 300 megawatt at 0.95 power factor? Is it possible to make it at means what to say 300 megawatt 0.95 power factor? If you do that, the voltage drop in the branch will be about 26 kV and your receiving end voltage go below the minimum acceptable voltage value. So I will plot the voltage drop as well, right? So right. So here the voltage drop is given, that is per phase. You need to understand that it is not per this one. Okay, into root 3 you need to multiply, then 400 minus root 3 into this, you will get 374. Somebody has talked about an angle before, so means what to say, sending end angle is 0, that is I have taken as a reference, and receiving end voltage is minus 12.92. So the real power always flow from higher angle to lower angle, and if you want to see megawatt MVR, yes, 300 megawatt is the load which is connected. The losses in the transmission line is 4.68. So I am drawing 304.68 megawatt from the grid. 98.6 MVR is the reactive power consumed by the load. The line is injecting 66.4 MVR. Please be remember this value is 152 MVR in the no load conditions, right? Why it is only minus 66 now? That is because the voltage has reduced and the current has increased. So the reactive power injected by the capacitance comes down because of the reduction in the voltage. If you remember a formula, Q equal to V square by XC or V square BC. So reactive power injected by the capacitor is directly proportional to square of the voltage. So reactive power injected by the transmission line, the shunt capacitance comes down, whereas the power flow increases. Previously it's only 220 amps, now the current is higher. So the reactive power loss in the inductance is more. So I mean previously the same line was injecting about 66 MVR, sorry 152 MVR. Now it is injecting only 66 MVR because of the loading of the line. So means what says 98 MVR is my requirement, 66 MVR is what the line generates. So I am drawing remaining 32 MVR from the grid. I believe that that makes a statement. So answer or a conclusion is, if your load is at, I'm not saying you cannot transfer 300 megawatt, you can transfer much higher power in 400 kV. But if your power factor is 0.95, then it is a bit difficult. So let me go, that also answers another ideal question. Your power factor has, even if it is even if it is I mean, so to say 0.95, your means what to say voltage will not be acceptable, or that means you may be accepting 0.8 power factor at 415 volt, you may not accept the same 0.8 at 11 kV, you may ask 0.9 or something, and you may ask 0.95 for 110 kV or something. But if you have 400 kV, means power factor should be as close as possible to per unit, that is 1 per unit. That's what the ideal requirements. So I'm keep on increasing the loads. Maybe I'm going ahead with maybe 600 megawatt, right? 600 megawatt at unity power factor. Yes. So here you can see means what to say the voltage drop is more. So maybe that's not really maybe possible. So let me put some other 450 megawatt. So please be remember, means you should not conclude that means you may not be able to transmit this 600 megawatt. It is possible, that depends upon what's the conductor which you are using and what's the line parameters which you have. Okay, so now I have used 450 megawatt at unity power factor. 450 megawatt at unity power factor. This 450 megawatt at unity power factor, your sending end voltage is 400 kV, your receiving end voltage is 390 kV. The angle separation is 19 degree. Probably this is what needs to be talked about, a steady state stability. When there is an angle separation, definitely you will be having a means what to say another subsequent buses, etc. So you need to ensure that the angle mismatch between one bus to any bus anywhere in the system should not go beyond 90 degree to ensure your system is steady state stable. Okay, now if you look at this, there is an interesting conclusion. The line loss has increased 9.8 megawatt. That's perfectly right. I mean, during no load, it was about 350 kilowatt. That has been increased to 4.8 megawatt or something when I have put about 300 megawatt load. Now, when I am increasing to 450 megawatt, the line loss has increased to 9.8. That's perfect. But you look at the behavior of the reactive power. The line was injecting about 152 MVR when there is no load, and the same line was injecting about 66 MVR when the load is about 300 megawatt. Now this line is consuming 7.96 MVR. This line is consuming 7.96 MVR when the line is with 450 megawatt. And if I have gone with slightly higher, this will consume more reactive power. So answer is, your transmission line can act as a reactive power source during no load or a light load, or when it is loaded less than surge impedance loading, and at more than surge impedance loading, means your line will act as a reactive power consumption device. So the same line will inject reactive power to the systems. It will inject reactive power to the system when lightly loaded or no loaded, or when it is loaded less than surge impedance loading. And if it is loaded above surge impedance loading, then it will means what to say consume reactive power. Yes, I think I have done with at least the first point what I need to cover. I believe there are quite a lot of questions. Why we call node as a bus in a power systems? It means it's a choice actually. Node and buses are one and the same. How to select a slack bus? It is quite easy. Means what to say, if you are an industry, you are getting a power supply from a grid, then you can take that substation as a slack bus and you can model it. But if you are modeling your entire country, then selecting the slack bus is a bit tricky. For that you have to go with the distributed slack bus model. So distributed slack bus model is not available in most of the simulation softwares, but still there are some simulation software supports a distributed slack bus model. You can check that. And slack bus is not the only concept to perform a load flow. There are many other methods which is available. So ETAP performs all the load flow only based on slack bus. So if time permits, tomorrow I will come up with the DIgSILENT power factory. It means the software has many other options to perform load flow. That's to answer Ram Natarajan. There is a question from Indu Govindarajan, why Newton Raphson is not used for load flow. Yes, you can use means what is it, Newton Raphson or Gauss Seidel as long as the system converge. But in a low voltage systems, your resistance value is more, so X by R is less or R by X is more. So that is called yield power system because the resistance is higher. So in a radial systems, it means what to say may not result in converging the results. That might be reason why you might be going for a forward reverse algorithm or etc. Or I will put it the other way around. I mean, what to say better than Newton option. It is there are many other simple methods which are available to find out your voltage profiles, losses, equipment loadings, etc. in the low voltage systems, which is radial in nature. Yes, per the current tariff plan, utilities are moving from kilowatt hour to kVR. That's a good question, Ganesh Kumar. Probably you can go back to our channel. We have talked about three videos on power factor corrections. I thought of covering power factor today, but by means of seeing the time, we may not be able to cover. You can very well watch. Means what say that answers your question. Why means utilities are moving uh, from kilowatt hour to kVR hour, not kVA or hour. It is a kVA hour. Means what to say. Means what to say that will not affect the simulation what I have done so far, but if you are performing means analysis for maybe an industry or metros or commercial buildings, then it will have an impact. Okay. Okay, Ajit, so question is analyzing load flow is okay, but is there any physical changes we may ask to reduce the line kilowatt losses to reduce the Ferranti effect? It is not analysis. So let me put it this way: means many people working in industry may claim that means what say real time is something completely different from theory. Answer is no. Means what is the simulation which we are doing here? This actually has to reflect in the real time systems. If you want to reduce the Ferranti effect, which I have not really tried it, but if for the sake of you, I can try it. There is no sun reactor which is available in ETAP. So what I am doing, I am replacing that with the means what to say uh, load itself. I am putting an 80 MVA reactor, right? Treat this as a reactor instead of load. So means what to say that helps you to means reduce the Ferranti effect, right? So means what to say if I don't have a load, you can see this is a Ferranti effect. So how to mitigate the Ferranti effect? By means of adding a shunt reactor. So I am adding a shunt reactor of 80 MVA. So since shunt reactor is not available in ETAP, I am using a lump load itself as a shunt reactor by means of giving 80 MVA with negligible losses. And what you got is a simulation of real simulation of what is the I mean voltage at the receiving end. So this is an example to mitigate. So answer to the question, Ajit, means what to say. This is the physical change also which you need to make. So load flow analysis, basically somebody has given a beautiful answer at the beginning when I have asked why do we need to perform load flow. In fact, I have not really touched that point. I mean, so load flow analysis is to be performed to validate the system, physical system which is running, and it is helping you to plan your future power systems. That's what somebody has stressed. I have missed their name, but they have perfectly identified that right answer. So load flow analysis helps you to plan your future. So it means if you are going to plan 300-kilometer transmission line, what is the shunt reactor which you need to put at sending end and receiving end, means you can identify using load flow analysis. That's to answer. Ajit, yeah, I think there are plenty of questions which are flying. I may not be able to answer all the questions. Let me take a few questions. What's the reason behind angle changes? Okay, that question can be easily answered by a formula like P equal to EV by X into sine delta, which you might be aware. So whenever there is a real power flow, I mean, what to say. Let me switch off and I will maybe take another example. I'm not sure this video is available in our YouTube channel, but we generally teach when somebody comes to our organization. This is the first. So real power always flow from higher angle to lower angle. If you look at this, even in the Ferranti effect case, 0.277 megawatt is flowing, right? This 0.277 megawatt is flowing from sending end to receiving end because sending end angle is 0 and receiving angle is minus 0.202. So real power will always flow from higher angle to the lower angle. And reactive power will flow from means what's a higher voltage to a lower voltage. Here you can see the receiving end voltage is 422 kV, sending end voltage is 400 kV. So reactive power flows from a higher voltage to a lower voltage. So to give a quick conclusion, real power will flow from higher angle to lower angle, reactive power will flow from higher voltage to a lower voltage. So here you can see real power is flowing from angle 0 to minus 0.0202, that is in this direction from bus 1 to bus 2, whereas reactive power flowing is from bus 2 to bus 1. That's because means receiving end voltage is higher than sending end voltage. And probably you can validate that also probably with the same example what I have done before. So means here I am making a means what to say Same voltage, same angle here, 400 kV angle 0, 400 kV angle 0. So there is no real power, there is a small reactive power which is flowing, that is 74.4 MVR. This is because of a nominal pi model what software adopts. So here, I mean, sort of say angle is same, voltage is same. So means what to say the reactive power injected by the line is equally shared between these two grids. Instead of this, if I'm say changing this angle from 0 degree to say example 5 degree, then you can really understand. I mean, so say real power flow will, you can easily understand. I mean, so say real power will flow from higher angle, which is at 5 degree, to the lower angle. So real power is flowing from bus 1 to bus 2 because bus 1 is at 5 degree and bus 2 is at 0 degree. So this is a higher angle bus 1. So real power is flowing from higher angle to lower angle. I believe that's clear. And if you want to validate, means what to say, reactive power also, that you can do. But before that, if I'm making it -5, you can see, I mean now the power flow will be just reverse. Yes. So mean this is at -5 degree, this is at 0 degree. So real power is always flowing from higher angle to lower angle. So if I am making it the angle equal and if I change the voltage, so instead of 100% voltage, if I make this voltage as example 105 percentage, then you can see, yeah, reactive power is flowing from higher voltage to a lower voltage, right? So means here it is means it means what the reactive power is flowing from bus 1 to bus 2. So I think yeah, that's perfect. Yes, so question is like somebody has put up time domain load flow analysis itself. No, time domain load flow analysis, you need to model your loads with respect to change in time. I cannot do this now at present, at least probably I will try. Means we do not have time domain load flow analysis model in ETAP, very frank. Okay, I will try if it is possible on Wednesday in DIgSILENT Power Factory. Right. So let me quickly go to other questions. There's a question from Satyanarayan Ramachandran. How do you set the criteria for modifying PV to PQ violation of the reactive power limits? Okay, that I have to means what's the answer quickly with respect to you. It means you need to go to the our generator model. Okay, in generator you might be giving Qmin and Qmax, real power minimum and reactive power maximum based on the capability curve of the generator. So when your reactive power limit hits, then automatically your PV bus will be converted into PQ bus. That's to answer Satya. And Sneha, why you use positive sequence shunt capacitance 0? Can we not make any sequence value 0? Yeah, that's beautiful, beautiful observation, Sneha. I appreciate it. So when I have, I mean, so what to say, done some analysis, I believe this I have changed it to 0. So it means your question is why not negative sequence and 0 sequence? Your values, your point is very valid. Load flow analysis takes only the positive sequence into the picture. Load flow analysis takes only the positive sequence because we are performing a balanced load flow. Balanced load flow, only positive sequence matters. Negative sequence and 0 sequence is not really matters. Even though if the value, whatever the value which you are changing, it will not affect the results. But whereas if you are going for an unbalanced load flow, right, there is something called that is optimal power flow. Yeah, this is a time domain load flow. Somebody has asked. We don't have that model. Sorry for that. And this is an unbalanced load flow. Yeah, this also we don't have. So if you're going for an unbalanced load flow, yes, then probably I mean, so to say, you can very well. I mean, so to say, use negative sequence and 0 sequence. But in a load flow analysis, it is a balanced load flow. So that means it assumes the sources are balanced, network is balanced, and loads are balanced, and hence positive sequence alone sufficient. But if your network is not balanced, if your load is not balanced, if your sources are not balanced, you have to go to unbalanced load flow analysis. For that, you have a separate model. But we have in DIgSILENT Power Factory where we can show the unbalanced load flow. That's a beautiful observation, Sneha. Okay. How to tackle the problem arises after load flow, which is critical, marginal, etc. So it depends upon what is the acceptable criteria of the voltage, what is the equipment loadings, etc. So now probably means when your voltage is within plus or minus 5%, that's fine. But if it is beyond 5%, then it is not acceptable. So then it is critical at 400 kV. But if you look at 415 volt, even means up to 10% is acceptable. So it all depends upon what's the criteria which the electricity board sets or the local regulation sets. That's to answer question from Abhijit. Yes, I think I have wasted quite a lot of time in my Ferranti effect. So let me quickly jump to another example of power factor. Right. So I'm not really going to this power factor in simulation. For that, I refer a video. Means we have power factor part 1 and part 2, which you can watch it in our video. But only one small conclusions what we can make is like, means what to say. You can see here I have put up a simulation itself. I believe screen might be very visible for you. Means we have taken a 2.5 MVA transformers in both the cases. Case 1 we have assumed with a 0.8 power factor. Case 2 we have assumed with a unity power factor. So here you look at this. Means what to say, the losses, reactive power losses, power factor at the grid, etc. So I mean with the 0.8 power factor, the losses is more, the voltage drop is more. So why do we need to correct the power factor? There are three reasons: to reduce the equipment loading, to reduce the losses, and of course to enhance the life of the equipments, etc. So means I'm not really going on all this. This is exactly which is available in our other sorry video, which you can really find it out as a power factor part 1. Yeah, power factor correction part 1 and the power factor correction part 2. We have done power factor correction part 3, but I believe somehow it has means deleted, but you can watch this power factor correction part 1 and part 2 at your time, and you can get really benefit out of it. Right. Okay. So that's about power factor. So because of a time constraint, I'm skipping that power factor. But anyway, that all relevant informations related to the power factor is available in a detailed manner for about 1.5 hours plus 1.5 hours, 3 hours video is available in YouTube, which you can watch. So let me go to the OLTC selection. Yes. So at least I will quickly touch that, and I will wind up my session because we have only 15 more minutes to go. Yes, so let me quickly take up an industry which receives the power supply at 110 kV and stepping down the voltage from 110 kV to 11 kV, and assume that the transformer rating is, example, 25 MVA. I am using oil natural air forced transformer intentionally to understand that in a transformer means you may be having a means different coolings, or probably you can relate this somehow. Okay, so if you want more information, anyway, transformer modeling is available, which you can watch, right? Yes, so means we have used 25 MVA transformer 110 bar 11 kV. I am performing a load flow without loads. So losses is nothing. Yeah, let me move on to the right side. Yeah, that will be easy for you. Yes. So sending in volt means the power supply where you are getting from the grid is 110 kV, and where you are receiving at the industry is at 11 kV. This is when there is no load. But even during no load, if the grid voltage fluctuates for any reason, assume that the grid voltage goes down to, say, example, 90%, then your industry voltage also goes down to 90%. That is 9.9 kV. So if you are putting it in percentage, you can put it in percentage. The voltage goes down to 90%. Please be remember, in a bus 4 where the industry receives the power supply, at that place itself your voltage is 90%. Means below this you might be having a cables and other switch gears, etc., and then you will be having a further cables and your motor will be connected. So the voltage at your motor terminal might be much less than this 90%. This is even the case of where there is no load which is connected, right? Okay, fine. Now let's connect a load. Assume the load is connected. I'm just modeling it as a lump load. I'm modeling it as a lump load. So the lump load is say, let me take 85 power factor is a good power factor to go. So right, I'm trying to load the transformer with a full load 25 MVA, which is not really practically possible, but still I'm trying. Yes, so here is the answer. So the transformer is loaded beyond 100%. LV side it is perfect, but means what to say, if you look at it in MVA, I mean why though I have connected 25 MVA, it is consuming 23.5 MVA is because the load what I have modeled is 80% constant power load and 20% constant impedance load. If you want to understand types of loads, again some videos are available in our YouTube channel which you can watch. Now I have made the load as a 100% constant power load, so the load is consuming 25 MVA. So when the load is consuming 25 MVA, transformer is loaded 25 MVA on the LV side, but it is loaded 27.3 MVA, much beyond its rating on the HV side. Okay, that's the real reason why I told, I mean, transformer cannot be loaded. Transformer cannot be loaded to its full capacity. Means including your losses, you can load your transformer only up to your rating. That's it. So now the voltage is further low. So then what is really needed to find out the OLTC range? So means what is, in order to regulate this bus 4 voltage where your industry loads are connected like motors, other transformers, etc. Means you need not really worry about the utility voltage, right? Means the industry is responsible, or industry owns the equipments in the industry, and the objective of the industry is to regulate the voltage of that particular industry, right? So means what say, I need not worry about this 90%, but I need to worry more on this 82.56 percentage. I need to bring within at least plus or minus 5 percentage, right? So in order to do that, what I can do, probably I can go with an on-load tap changer. On-load tap changers are always provided on the high voltage side. Either it is not in the primary or secondary, it is provided on the high voltage side, and it always regulates the voltage of low voltage bus. I have given a tap of plus or minus 10 percentage with a step of 1.25. At least I believe the people, those who are from industry, will be able to understand that. Yes. Okay. So probably you can see, even with an on-load tap changer, means I am unable to bring the voltage within plus or minus 5% tolerance. Right? Even with an on-load tap changer, I am unable to bring down the voltage within plus or minus 5% tolerance when the grid voltage goes down to 90% and I have a full load. So then, I mean, this is what precisely I have touched at the beginning. Purpose of load flow analysis is to find out what's the optimal tap range. So I am changing this minimum tap to minus 15 percentage instead of 10 percentage. Yeah, now you can see the voltage is 99.87. So if you want to know, I mean, in which tab it is, I'm able to achieve this results, that's available if you select update transformer LTC. Yeah, yes, somewhere you might have seen the tab. Yeah, this is achieved at exactly at minus 15 percentage tab. Right, so if you go to minus 15 percentage tab, you will be still able to maintain the voltage close to 100 percentage when even if the grid voltage falls to 90 and the load is fully loaded. So I believe that has given you an idea of means an interesting idea of how to select the OLTC range. Only one side I have selected, that is on the minus side. Similarly, you can really work out when the grid voltage is maximum, that is like 110 percentage or something, and when the load is minimum, what's the positive side which you have to develop. Say example, if your industry maximum, say example, goes to 110 percentage, say, then with an OLTC you will be able to perfectly maintain the voltage that is at plus 3.75, and assume that means what to say, if means load is not there, still you will be able to maintain 100% voltage with a plus 10% tap. So means if you're okay with plus or minus 5 percentage tolerance, then very well you can go with minus 15 percentage tap and plus 5 percentage tap, and then that's how we have to select. Yes, I think means I will be able to take it up. Means some good questions. Time is 10:53. I cannot definitely extend the session beyond 11. I definitely respect your time. So 7 more minutes. Anyway, I believe feedback link is already shared. Hope you got the feedback link. I'm coming back to the slides, but yeah, you can very well. I will take up some questions. Yes, there's a question from, yeah, feedback link. I think I believe we have set it. We will go to the discussions of yeah. There is a question from Ravichandran. There any capacitance between the lines? I'm not sure what you mean by that, Ravichandran. Answer is, means what to say. Whenever there is two different voltages separated by an insulation medium, then you will get a capacitance. So that means the capacitance not necessarily mean this is a capacitance between your R phase and the ground. This is also between R phase and Y phase. So if that is your question, answer is yes. I mean, so to say, definitely there is a capacitance means which exists between the phases, R phase and B phase. Yes, definitely there is capacitance. And if you talk about lines, if you mean a double circuit, yes, means what to say, again R phase of one circuit mix up with all other phases in the same circuit as well as all other phases in the other circuit, that also there is a capacitance exist. So these are all the things which can be validated using simulation softwares like ETAP or even PSCAD if you want in more detail. Another question from Sheikh Hussein: what's the effect of unbalancing under transposition? Yes, if you're not transpositioning your transmission line, then means what to say, your capacitance and inductance on each phases will not be same. So R phase current, sorry, R phase capacitance will not be equal to Y phase capacitance, which will not be equal to B phase capacitance if it is a vertical line, and if it's a horizontal, it's means both inductance and capacitance, and hence this will result in a unbalance in the voltage as well as the current. If you transposition it, then you make RLC parameters equal for all the three phases. So there will not be any unbalance in the transmission system. As I talked about, there are three unbalances. One is the source unbalance, which occurs in the generator itself. There is a second unbalance which occurs in the network, which is what we are talking about to transmission line. And last one is a load unbalance. That I believe that's perfect. Sake, I believe you will be able to get much more details on this effect of transpositioning and unbalance in our transmission line modeling in our YouTube channel. There is another question from Ghost. While doing power factor improvement, which one would be more efficient design? Keeping capacitor bank and the main panel or individual sub panel? It's a techno-commercial decision goes. So means what say, technically it is advisable to put up reactive power compensation at each and every place where the reactive power is consumed, but that's not commercially attractive. So definitely you have to do a techno-commercial evaluation to identify uh, there is means what to say, you can identify what's the capacitor rating which you can select, and where to select, how many capacitor banks, whether it is an automatic power factor correction or not, means whether you need a dynamic compensations. All these things you can do with a detailed analysis, right? And there is a question from Priti Goswai. What will happen if we have two different vector groups of a transformers? You can very well go ahead with the two different vector groups. You cannot parallel it. And I believe we have also talked about a transformer paralleling in one of our video. So if you have two different vector groups, you cannot parallel the transformers. But in a radially working, it's not an issue at all. There is a question from Rajesh. While running the load flow for the time standard bus systems, I am getting the results at each and every bus. How to verify the answer is correct or wrong? Okay, so probably you can very well validate that using a manual calculation, or you can go with another simulation software to validate it. That's not really an issue, right? Fine. Is there any other questions? If I believe I will be able to take. Maybe one important note, I think, means what say, the session is not over today. The session is basically a means 3-day session. You can have the session tomorrow morning at again at 9:30. So we have sessions 9:30 to 11, 9:30 to 11, 9:30 to 11 on today, tomorrow, and day after tomorrow. So today and tomorrow, because I have another session at 11 o'clock, I may be shortly winding at 11. But if needed on Saturday, probably I am available. We can extend the sessions even after 11. I believe there are about 500 plus participants are watching. Definitely, I have to give means what to say, a big thanks for all of you for watching the sessions. And I believe I have added a little bit value, at least if not the great value to you and your time. And if you have any questions, please feel free to post it. And somebody is asking a question, feedback link for students. Means I believe this is for an all. So you can very well fill the forms even if you are a student. There is an option, I believe, or else probably the administrators will definitely correct that, and you can fill the feedback forms. Yes, what is the total points in the feedback form? Really, I'm not aware. If organizers are there, they may be able to answer that. Okay, and please post all your questions. I'm definitely going to take all the questions. I will definitely take out all the questions in the offline video. Then I will try to answer all your questions tomorrow. Right, I have just a minute to go. Thanks a lot for SSN College organizing such a wonderful session. And I strongly believe, I mean, 500 plus audience is not a really a small number. Thanks, and people are watching even after posting the feedback link. That means, hope you have learned at least a bit from me. Thanks a lot. We want you to be back sharply at 9:30. We can even start at 9:25 tomorrow. Thank you guys. Thanks a lot. Have a nice day. Enjoy the days. We will meet again at tomorrow. Thank you.